Now, all simple harmonic motion will continue for a very long time. Theoretically, it would continue forever. However, there are other forces involved. In the case of a spring, you have internal friction of the spring itself. In the case of a pendulum, you have air resistance, so on. And so we have, so the harmonic motion will not continue forever. So in this video, we're going to look at damped harmonic motion. So damped harmonic motion is just simply harmonic motion that has this external force and causes the amplitude to decrease over time. And so you can see here a graph of simple harmonic motion, but the amplitude is always decreasing. And you can actually see that the amplitude follows this nice exponentially decreasing function. And that's quite typical of all damped harmonic motion. Now, there are three ways that harmonic oscillations can be damped. The first is called underdamping, where there are a few oscillations before it comes to rest. So you have your oscillator comes down, goes up, and then just kind of dies out over time. So a classic example of this would be, say, you're in an old truck where the shocks are gone, or you have springs under the seats or something. You hit a bump, and then your seat just bumps and bounces up and down and up and down and up and down, gradually dissipating until it stops bouncing. And then you have the critically damped system. A critically damped means that the damping force is just right, that the oscillation starts, but then very gradually brings you back to an equilibrium position. So this is the fastest way to get to equilibrium, and the softest, I should say, as well. For example, you're in a car, brand new shocks, really nice. You hit a pothole, you barely feel it. Why? Because those shocks are critically damped. It causes that oscillation to disappear very fast. But last but not least, you have overdamping. Overdamping is not fun. Basically, you have things very, very tight. It takes out the oscillation right away, so instead of pushing it towards equilibrium right away, it just stops it and doesn't move very fast. Then very gradually it'll come back to equilibrium. Good example of this would be riding a bike. Bikes have no shocks. And so if you're riding a bike that has no shocks, you hit a pothole, you feel every single bump. You feel every single pebble, pothole, change in the surface, whatever. You can feel it all. So that would be an example of overdamping. Now, there are systems where damping is unwanted, such as clocks and watches. We want the clocks, like if you have a grandfather clock, we want that pendulum to go on forever. Watches that have gears and harmonic motion inside to make it run, we don't want them to stop. We want them to keep going. So we want very, very little damping. But there are other systems where we do want damping. And when we do that, we want it as close to critical damping as possible. Car shock absorbers, you want that to be, the damping to be close to critical damping. Otherwise, you're going to feel the potholes, or you're going to start bouncing up and down and be out of control. Earthquakes. We are building shock absorbers for buildings now. And these shock absorbers have to be near critical damping. If they're not, then if they're underdamped, then it's going to allow the building to shake and move around, which will cause a lot of interior damage. But if it's overdamped, then that makes the building too rigid, and if it's too rigid, then things can torque and come out of place and break apart. But if it's critically damped, then the building can sway very gently, but any oscillations in the building itself can be cut out. The the oscillations will be damped as quickly as possible, thus minimizing the damage in the middle of an earthquake.